Welcome to the Adirondack Sky Center and Observatory. There's nothing more inspiring than the night skies in the Adirondacks. It just makes sense to start your visit to the wilderness above with us. Our current programs focus on immersive experiences for audiences of all ages. They reach as close as into our own community and as far away as students from around the globe. From inspiring presentations given by some of our friends as world experts to our Keystone 4-day Astrophotography conference, there's something for everyone, including live as well as virtual stargazing, customized programs for schools, and private events. In the case of the Adirondack Sky Center and Observatory, the sky is certainly not the limit, but only the beginning. A second building is currently in the planning stages in the form of an Astro Science Center and Planetarium. This 18,000 square foot building will be dedicated to the study of astronomy and space travel. The planned $15 million Astro Science Center will feature a state-of-the-art planetarium under a 30-foot dome, a 100-seat theater, and a large area for hands-on and interactive activities. Our many exhibits will include a Foucault pendulum, overhead models of the solar system, and historical permanent as well as traveling collections. It's our mission to make this an immersive experience for everyone. You will never be told to look and don't touch. This new building will be in addition to our existing roll-off roof observatory, which houses 4 permanently mounted telescopes. The final phase of construction includes a traditional observatory dome housing a new 22-inch research-grade telescope. Please contact us to become a member or make a donation to help build this new Astro Science Center and Planetarium and begin your journey to the wilderness above. And there you go. You've probably heard us talk somewhat about the new Astro Science Center and the planetarium, lecture hall, classroom, activity room, or whatever we're going to be calling it. If you haven't picked up my background, if you can see my my screen, that is a rendering of what the new building would look like, or at least similar to that. We met just a few days ago and had some really deep conversation about the exhibits that will be in there, the design of the planetarium, right down to lighting. So this project is moving forward, and we are anxious to get more folks involved. So again, if you're interested in making a donation, feel free to do that. If you're interested in an investment opportunity, we are also very interested in talking to you more about that because the planetarium has not been named yet. So imagine the Josh Thomas Planetarium, you know, if Josh makes a sizable donation to us or anybody out there. So again, please consider getting in touch with us to talk more about that. We'll be happy to spend as much time as you like talking about our new Astro Science Center and Planetarium. In other news, coming up soon in October is our Astrophotography conference. This is a 4-day, all hands-on, super immersive experience. So if you're brand new to astrophotography, if you've been thinking about getting into it, this is the place for you. If you have if you're experienced and want to improve your skills, either in acquiring the images or processing the images, you can see there in the upper left, the left corner of the screen of that image is an aerial view of some of the participants on the field at the roll-off roof observatory collecting data. And what you can't see in that picture necessarily are all of the instructors right around everybody, helping them hands-on set up their cameras, do all of the technical stuff in the field. Then over on the right side of this poster, you see that we go into a classroom, a computer lab, and we help process all of the images. So whether you're brand new to it or been doing it for years and want to improve your skills, this is a once in a lifetime, or actually we have many repeat attendees. So for $300, a 4-day experience, you will not regret coming to this if you're interested in any way in astrophotography. So that's enough of that stuff. What I want to mention again is that our microphones are muted. We'll have some Q&A after tonight's presentation. And of course, our presentation tonight will be posted on YouTube within a day or two, as all of ours are, going back to the original Cygnus series way back in 2000 or maybe before that. So feel free to take a look and explore some of those previously recorded talks that we've done. If you've just come into the room, if you wanted to enter or open up your chat from Zoom and just let us know where you're calling from or where you're viewing from, it's always kind of interesting to see that. Additionally, we will be putting some links into that chat box for you, so that'll be helpful. I think Josh is going to add some stuff in there too, possibly throughout the course of his talk. So on that, stars from birth to death. That is a great topic tonight by Josh Thomas, a associate professor, recently appointed associate professor, or promoted. Congratulations to Josh, the director of the observatory in the Department of Physics at Clarkson University. Josh obtained his doctorate in physics at the University of Toledo in 2012, which is the state in which he was born, in Ohio. His research area is astrophysics, and his specialty is observational stellar spectroscopy. Josh also has experience in accelerator-based atomic physics and computational astrophysics. He draws on his this breadth of experience in advising many undergraduate students in research, as well as in public science outreach. Recently, his focus has been on studying various types of binary stars at various stages of his life. We like him because he's a member of the board of directors for the Adirondack Sky Center and Observatory, and he does these talks for us regularly. So with that, welcome Josh and Stars from Birth to Death. Take it away.
Thank you, Seth. PowerPoint, there we go. And just a moment to push all the buttons and be ready here. As Seth said, you can read the title of my talk there, Stars from Birth to Death, and my name is Josh Thomas. And I'm looking for the little, I want the little laser pointer. There we go. Perfect. All right, so you've seen enough of my title slide. So what am I going to talk about today? Just maybe a little bit of a background. I took all of my slides on the lives of stars and put them together and added a few and realized I had like probably a week's worth of lectures. So I have chosen one particular little storyline to tell through this, and so some of you may know some of this, some of you may not. So hopefully everyone gets something out of today's talk. So we'll talk a little bit about what is a star, and we'll start with the closest star to Earth, which is our sun. And we'll spend a little bit of time talking about the classification. And the classification, and for those that know the HR diagram, are really the backbone of this presentation. And so then everything else follows from there. We'll talk about how stars are formed, and then we'll talk about how they change in time or stellar evolution. This does not mean stars are growing legs, just means we're talking about how things change in time. And we'll talk about two categories of stars there, low mass and high mass stars. And if there's still time and I haven't put you all to sleep, we'll talk about binary star evolution, which is even cooler. And you can see a nice little word cloud here of a bunch of things that you might key vocabulary words that you might hear today. And you might want to memorize these because there's a test at the end of today's presentation. Just kidding. So the sun is a mass of incandescent gas. I'm not going to sing the rest of the song. But if, for those that don't know, there is a They Might Be Giant song with some relatively accurate lyrics about the science of how the sun works. And if you haven't heard this song before, it's required that you go listen to it after this presentation. So our sun is a giant ball of mostly hydrogen, followed next in abundance by helium gas. And this giant ball of gas is glowing because it's producing energy. You see Einstein's infamous equation there, E equals mc squared. I once corrected a television interviewer because he said E equals MC2. And I'm like, we went off air and I was like, it's E equals MC squared. And he's like, that's what I said. And I'm like, not really. So anyway, C times C. Speed of light's a very big number for those that don't know. So what this means is if you take a little bit of mass, multiply it by the speed of light squared, you can, that would equate to a very large amount of energy. And it's that energy that is the source of light and heat in the sun. And this all comes from the nuclear fusion process called the proton-proton chain, where we take the net reaction is 4 hydrogen and we smash them together through various collisions and we get helium. For those that don't know, I'm being a little loose here with the terminology. It's really not hydrogen, it's really protons, and that's where the whole proton-proton chain comes from. Hydrogen's the first element, it has 1 proton if you're talking about H1. And if it's an atom, it has an electron. But if you heat it up enough, that electron gets stripped away and you're left with a proton. And so we're really talking about smashing these protons together. And you may or may not know that protons are electrically charged. And you know a little bit about electric charge if you live anywhere in a part of the world where it gets a little bit dry, and you scuff your feet across the floor with your socks on and you zap your sibling. That is electric charge, right? So it turns out that if you have 2 things with the same charge, you probably learned this in kindergarten, as the science professors usually say. And if you take 2 charges that are the same and you try to push them together, they want to push apart. So in order for something like our sun to actually be doing this fusion process, these protons have to be moving fast enough for them to actually overcome what's called the Coulomb repulsion so that they can actually smash together. So what does that mean? It means you need really high temperatures. And the little note at the bottom, brown dwarf, was a note for me to remember to say here, that the universe is full of a continuum of objects, from little clumps of atoms to grains of sand to asteroids, planets, brown dwarfs, and stars. And so the dividing line that we've drawn between the classes of objects here that we call stars versus brown dwarf is that brown dwarf stars, sometimes we say that, do not have the high enough temperatures at their core to fuse hydrogen into helium. They might be able to fuse deuterium, but that's a whole other discussion. So save that for maybe another talk. The picture on the left is right, which I don't know which side that is, right on my screen, is from the 2017 total solar eclipse. All right, so there are other types of stars, other words that we might come across. So there are stars that look close to each other on the sky, like in this image here, and that could be, usually is, just an optical double, meaning that these stars are actually different distances from Earth, as you can see in this other picture that my laser pointer is trying to point at. And they just happen to be close to each other on the sky. So I can take my hands here and put them at different distances, but on the screen, they still look like they're close to each other. That's a really common thing in astronomy. And actually, for those of you that remember back in December, we had the conjunction of Jupiter and Saturn. This is the same thing. They were close to each other on the sky, but they were still very far from each other. We also have visual binaries. These are a little less common, but if you can point a telescope at them, see the separation between them, and you can actually watch them orbiting each other. What's far more common is that if we're talking about binary stars, and binary just means 2. So anytime you have 2 stars orbiting each other, I'm talking about a binary star system. And so non-visual binaries, these are things like spectroscopic binaries, where the fact that there are 2 stars there has been determined through some means other than looking at it. And that's also a discussion for another talk. In fact, you can go to the Cygnus series from August 14th, 2020, where I talked about spectroscopy. You can go back to that. So here's a lovely globular cluster that's in the armpit of Hercules, M13 as it's sometimes referred to. And what you see here is this absolutely stunning collection of stars. So globular clusters, just where a bunch of stars happen to live together. They probably all formed together, and we'll probably not talk too much about the details there, but the key thing that I'm showing this picture for is that I hope that you're picking up on the subtle detail that the stars are various colors, but not all the colors, right? I see blue, I see white, I see red, I see yellow. There are no green or purple or puce stars, right? So what's up with that? And so we'll talk about that in a few slides. I forgot the order of my slides, apologies. So the next thing I wanted to talk about in sort of our background here is how is our sun? What are the layers of our sun? What is it made up of? You know, here on Earth, we've got a crust and we've got a core and the mantle and all those things. And we have similar things on the sun here. So the part that we see of the sun is the photosphere, kind of like photograph. So hopefully that makes sense. Everything above the quote surface of the sun is what we call the atmosphere. So these layers, photosphere, chromosphere, corona. Inside the sun, well, the inside of a star depends on the type of star, it turns out, and I don't want to spend much time on that today, but basically for our sun, we have inside this convective zone. Deeper down, we have this radiative zone, and all the way at the center of this cutaway diagram of the sun is the core, and it's in that core only where the temperature is high enough for fusion to occur. And then the light makes it from the core to the surface of the sun, takes about, I forget the order of magnitude, if it was millions or billions, but anyway, it takes an incredibly long amount of time for the light to actually get out. So the core, the size of the core, the temperature of the core is all set by the mass of the star. And so mass is the fundamental property that sets what a star ends up looking like. So the only real overly sciencey word that I think, well, they're probably all overly sciencey, but the one that I got here as a definition is hydrostatic equilibrium. And so equilibrium, that means things are in balance. Hydrostatic, maybe a weird misnomer, but hydro means water, static is not moving. So a not moving equilibrium. So what does this mean? Well, we have pressure from the inside of the star pushing outward. This is radiation pressure. It turns out light can push on things. If you know anything about some future space mission ideas, there's something called a solar sail, and that works by light pushing the object, accelerating it very slowly over long amounts of time. That is actually the force that's actually pushing outward in the side our own sun. So that would be the arrow pointing out here. Then you also have the inward pull of gravity because this gas has mass. And so if it's all balanced, you can see these three black dots in the cutaway of the sun here. The arrows are the same length, and they're in opposite directions. So that's where the balance comes from. And thanks to Pixabay, I found this picture of some dogs playing tug of war. And I labeled them gravity and radiation. So maybe someone can have a pair of dogs and name them gravity and radiation, just because they watched this talk. But if both dogs are pulling it the same way, right, then the rope and the dogs don't really move. But if one pulls harder than the other, then obviously that moves in one direction or the other. So we'll talk about this more. This is the fundamental thing that guides how a star lives its life and how it changes over time. And so we'll talk more about that in the rest of this talk. The thing we see, the surface of the star, is the color of that is actually set by the temperature. So there's something called color temperature, if you want to take a look at that. But this is also sometimes called black body radiation. And this image down here is a flame heating up, will look like an iron spike or something. And the flame is nice and blue. and the metal is sort of this yellowy color, and then it goes down to sort of red, and then it's not glowing. So you probably know that the flame is hotter than the iron. So blue means hotter. Yellow there is sort of, somewhere in the middle, and red is the cooler color. And that's the exact same thing that happens with stars. And so when you look at this picture of M13, you see red, you see blue, you see some yellow, and that all corresponds to the brightness here on the vertical axis of my graph versus wavelength. And the vertical black lines here mark the part of the spectrum that our eyes can see. B and V, for those in the astronomy know, are the B and V filters. Don't worry about that if you don't know what I'm talking about. And we'll talk about the classification of stars, but it turns out the hottest stars are O stars, the coolest stars are M stars. And it turns out that the slope of this line through the optical part is what sets the color. So if the star is brighter on the blue side, it looks blue. If it's brighter on the red side, it looks red. And if it's kind of shallowly sloped, it's sort of yellowy, okay? And that's our sun is in that situation. Our sun is a G-type star and sort of yellowy. Okay, so that's temperature. So that's the surface of the star here. I'm not talking about the core now. I'm talking, this is the surface temperature of the star. And so there's a temperature classification. I already told you O is the hottest stars. So old bald astronomers frequently give killer midterms is the mnemonic that I made up when I took my class years ago. And we have spectra here sorted by spectral type of star on the left of the little nice rainbows here. And those are spectra. Go see my last talk on that if you want to know more. But basically, this corresponds to this. There's a little bit of subtle difference. And if you want to know more, I can address that later. One nice pair of stars that we often see if you come and observe whenever we can do that again. Here, Alberio is a nice blue star and red star next to each other on the sky, most likely an optical double. Maybe it's a binary. I think the jury is still out on that. And then I wrote in parentheses LTY, because you can take the same idea of classifying things by temperature and apply it to brown dwarf stars, which are not fusing hydrogen into helium. So the language gets a little confusing. Okay. And the other big thing that we need as a tool in our toolbox to understand stars is the Hertzsprung-Russell diagram, or lovingly called the HR diagram. On the vertical axis is brightness. In this case, sometimes these are in various different units. In this case, units of the sun's brightness. So 1 is where the sun's at, right over here. And on the bottom axis is the surface temperature. Now, if anyone in the audience is familiar with graphs, you'll notice that the bottom axis is weird. The highest temperatures are on the left, the lowest temperatures on the right. I didn't make the graph. That's the standard. This is how it's made. This is what I use. I liken the HR diagram by analogy to stars. It's like the periodic table for elements. So I can look at an HR diagram and know a bunch of stuff about what a star is doing. So there's this big long path that runs sort of diagonal-ish. It's not quite a line. That is what we call the main sequence. And stars that fall there are stars that are fusing hydrogen into helium. That's what makes them main sequence stars. And then you can see the other categories here, giants and supergiants. And then white dwarfs are also shown on this graph, even though they're not fusing anything. And we'll talk about that a little bit later. And the sun is a G2 Roman numeral 5, if you want to use this system that people use. So 5 means main sequence. G is the temperature. So if you go over here, you can find G. I added the letters here, so they're not necessarily in exactly the right place. And the 2 is just a finer microscopic view of the temperature of the star. Those numbers go from 0 to 9. And so this is our sun is a G2 type star. So, all right.
Josh,
So,
what is the indication of that red star down at the very bottom there in the lower right-hand corner of that graph?
Oh, it says AB Doradus C.
Yeah.
This thing.
Mm-hmm.
Yeah, so that's an excellent question, Seth. Thank you. And actually, this is a great point. And there are 3 M stars. If you go up vertically here, there's 3 luminosity classes or brightness classes of these stars. We have AB Doradus C would be an M5, an M Roman numeral 5. I don't know about the number, the 1, 0 through 9, but it would be an M Roman numeral 5 star. A giant star would be an M Roman numeral 3, and a supergiant would be M Roman numeral 1. And I can't remember if I kept the slide in that shows a few of these, but they have different brightnesses, but the same surface temperature. And you can see that there are also some blue stars on this diagram that have the same situation, that there are blue main sequence stars, but there are also blue supergiant stars. And so that's a really good point. Thank you for reminding me to say something about that.
Oh, you're welcome.
All right. Maybe. The pointer is very slow, so I think my computer is overheating. There we go. All right, so I didn't want to spend too much time on this particular slide. Just, this is from Wikipedia. I flipped it around the other way so that it goes highest temperature on the left to lowest temperature on the right. These are the relative sizes of stars only for the stars on the main sequence. And the other thing that's really interesting to point out is how long they live. So this the numbers are from Wikipedia. I stole the images from Pixabay, and I drew the lines on this. So high mass stars are O and B type stars, and they're very hot and they're very massive. So we also measure the mass of stars relative to the sun. So one solar mass would be the sun, and in this case, an O3 star, an O3 Roman numeral 5, since these are main sequence stars we're talking about, would be 60 times the mass of our sun. It's a little hard to think about. But because they have more mass, it turns out their core temperatures are higher, and it allows that fusion to happen much faster. So in my analogy, it's like a Hummer. You can fill the tank up, and it goes a little ways, and then you have to fill the tank up again. And then the bottom one, I used to say a Prius, but I decided, well, okay, I drive a Subaru. It gets pretty good gas mileage, so I'll use a picture of a Subaru. You can go farther on a tank. That's the mental image I was trying to get across there. So these stars live, if you want to use that term, a longer time, meaning they spend more time on the main sequence, fusing hydrogen into helium. And I also want to point out, when we talk about the various stages of a star's life here, so we've got main sequence and giant and supergiant. We've also got protostars, which I didn't mention yet. Stars spend most of their time on this main sequence. So you can see O stars only live for about 3 million years, which is a long time for us, but for stars, that's a really short time. I mean, the Earth has been around 4.5 billion years, and therefore our sun, because we most likely formed with our sun. The sun can live estimated fuel tank lifetime of 10 billion years. And these little M stars, which are very numerous in the universe, have lives so long that the age of the universe is actually a fraction of the total time they could possibly fuse. Just so you know, the age of the universe is currently measured to be about 13.7 billion years old. So I think that's kind of interesting. So when we go forward, we're going to be talking about high mass stars and low mass stars, and we'll start with the low mass stars just because. And maybe we'll change slides. There we go. Oh, and a nice little size comparison of the sun, which is this little pixel, and the largest known star, VY Canis Majoris, and it's a big gobbledygook name, but basically just means it's in the constellation of Canis Major, and it's star VY. The Earth's orbit is shown on here as well, and you get a real sense that these stars can be quite big. So let's talk a little bit about star formation. I see I'm at 24-ish minutes into my talk. So star and planet formation, they really form together, and you really kind of have to talk about star formation when you talk about planet formation. So in the textbook I use, that's how they present it, and I really like this view. So here's a Hubble Space Telescope image of the pillars of creation, which is the visible part of the spectrum, and it's most importantly what's called a cold molecular cloud, and I'll talk more about that in a moment. And if we zoom in on these regions shown, we see what turns out to be little baby stars. Sometimes we'll say protostars. It turns out these are also sometimes called T-Tauri stars. And here is a picture changing in time. So this is many observations over time of something just like this. And what you see is this sort of like little weird shape. And what's going on there is you're seeing light from above and below a disk, and then the little, looks like a black bar in the middle is actually a disk of material around that star forming planets, and I'll show you some more of that stuff in just a moment. And then the stuff coming out the top is a jet. So as these stars form, you'll see that the jets are sort of a common thing. Now, cold cloud is important because what do you have to do to have a star? You need to have a bunch of mass in one place. So how do you attract, how does one hydrogen atom attract another hydrogen atom? Well, they don't have very much mass, and they need to attract each other by gravity, because normally they want to repel each other. Well, I guess if they're neutral there, but anyway. So in this case, we need them moving slow enough so that they can gravitationally attract. If they're going real fast, the gravity is not going to pull them together. So one of the things you learn in chemistry way back, if you had chemistry, or in the future, if you're going to take chemistry, is that slow things are cold temperatures, fast moving particles correspond to high temperatures. So you need cold clouds of gas so that gravity can pull things together. And once that happens, all the cool stuff begins. So imagine you have a cold molecular cloud. Gravity starts to attract little pieces, little atoms, a little more, and you start growing these little dense regions of your cloud. These are at this point still just gas, you know, hydrogen, helium, and a smattering of the other elements that make us up. This continues until you start to get little more dense molecular cores, molecular cloud cores, sorry. And so I put a little box, and we're just going to zoom in on one of these. And so you have this little dense core, but everything is forming probably in our own galaxy, and the galaxy has a little bit of motion, a little bit of rotation. So as these clouds form, you start from a big cloud and they're collapsing to a more and more dense state because under gravity. But what happens when you take something that's rotating very slowly and collapse it, it starts to rotate faster. And you see this in all of the amazingly awesome sports, whether it's diving or figure skating or ski jumps, all of those things where athletes are starting in some sort of extended position, pulling their arms in, they spin faster. When they want to slow down, they put them back out. This is the same physics that happens here. So as this happens, you end up with a more and more rapidly rotating star at the center, growing, slowly accumulating material through some more complicated physics I do not have time to explain. You end up with a disk of material. And that's, and I'm sorry, I keep having trouble switching to the next slide for some reason. And that's where you get your forming star, and then by extension planets. And on the left is the model, and on the right are real images taken, in this case with Hubble, of actual forming star systems, T-Tauri stars with their circumstellar environment, if you want to use big fancy words. And this has been in the news lately. So the ALMA, the Atacama Large Millimeter Array, which is in Chile, just recently released this disk around a star. So this one's actually tilted. The previous ones we were looking at are what we would call edge on, like my hand is right now to my camera, versus face on. So this one's kind of face on. And what was newsworthy about it is that we see what's most likely a planet forming with its own little disk, forming potentially its own little moons, which is something how we might imagine Jupiter formed with its giant moons. So I can put the link. We'll see if I can do this. I'll try this. Yep, copy. I think my computer's having a hard time, actually. There we go. So I pulled that from this Earth Sky article, if you want to know more. So it turns out the closest place in the universe to the Earth, which is forming stars, is right near us. It's called M42, or the Orion Nebula, which is this gorgeous molecular cloud with a bunch of bright blue stars. These are all O stars. And then down in these cloudy bits here, we have more stars forming. And for those of you that don't know, this is in the constellation Orion. And if you look at Orion and his belt and go down to his sword here, the middle of the 3 stars here is in fact not a star. It's this nebula. You can see it with your own eye or a pair of binoculars or a small telescope. So check that out sometime if you haven't already. And then you can go to the Astronomy Picture of the Day archive and get all sorts of really awesome visualization, 3D visualizations and other pictures. And I just linked a whole slew of those things here. Check those out. I knew I wouldn't have time to discuss them, so I'm going to move on. So that's the closest star forming region to Earth. All right. So promised life of stars. So we have a low mass star. Low mass star is something like our sun. So what will happen to our star from birth to death? So here's a little overview. You'll see this a couple times. We're on the low mass stars, so we're down here at the bottom. And so we're going to talk about, so there's brown dwarfs, but we're not going to talk about them. We're going to talk about stars and how they change over time. And so you can see we've got birth, main sequence, what they call old age, death, and then what's left over, the remnant, the corpse, if you will, if you want to use that analogy. So again, here's our HR diagram. It turns out those T Tauri stars, or those protostars, actually start as very red, and actually they're brighter than the stars they end up becoming. And so they start and they move sort of down this way towards the main sequence where they spend the majority of their life. When they use up their hydrogen, now we've got a problem. Remember the dogs, gravity and pressure, radiation, gravity and radiation, the 2 dogs, right? So the hydrostatic equilibrium, the balance, is what sets the size of the star, and that's all set by the mass. But I left out a little piece. Remember, you need that energy. You need that radiation from the nuclear fusion to be pushing outwards. So if you suddenly use up all of your hydrogen, then you can't push out. So what does the star do? Well, initially, the inner part of the star starts to collapse. So the core can't support itself. So the core shrinks down. The core shrinks, and then what happens is the layers above it also shrink. Well, what happens is you end up with the layers that are above eventually getting to a point where they shrink, become hot enough, now they can fuse. But here's the interesting twist. You end up with more fusion in this shell around the what the little diagram here calls a degenerate helium core. So you're fusing hydrogen into helium. You end up with a helium ball that's not hot enough to fuse, so it shrinks. The upper layers shrink down, get hot enough to fuse, but now you're making more radiation. So suddenly radiation is pushing a lot. So the star gets bigger. And so in the red giant phase, the star actually swells up. Meanwhile, you have this core that's not fusing and then a shell of hydrogen that is fusing. All right. So this is sort of the big overview, and I initially had a bunch of broken down slides, and I figured if I had all of those slides, we would be here until tomorrow. So this is the one shot all at once. So you're on the main sequence, you're fusing your hydrogen into helium. You use up the available hydrogen in the core. So you become a red giant. And this continues. You end up getting brighter and brighter and brighter and brighter as the core shrinks. The shell is burning. But what's the shell doing? The shell is converting hydrogen into helium. That helium is going to sink to the center. And so basically, it's like watching a fire, right? The ash builds up. So this non-fusing helium core builds up and eventually gets to the point at this little top part here where suddenly there's enough pushing down, enough gravity pulling in on that helium that suddenly it can fuse. But it turns out for these low mass stars, it turns out that happens extremely quickly, called the helium flash. And so suddenly the whole thing is fusing. You get this drop down in brightness of the star. The whole star shrinks as gravity now pulls down. And you get this little, almost like a short reprieve, where now you're fusing helium into the next element that happens when you do fusion, which is carbon. So you end up making now a carbon ball at the center of your star that's not fusing and contracts. And then you end up with a hydrogen burning shell and then a helium burning shell. Sorry, I said that backwards. It's an inert carbon ball, a helium shell, and then a hydrogen shell. Sorry. So now you'll notice in the little diagram, this is what they call an asymptotic giant branch star. So you go up the branch, we call this a branch for some reason. And then you go it up again, but this time you go way higher because now you're fusing hydrogen to helium, helium into carbon. You've got a lot more energy. So the size of the star swells up more than it did before. Now, what ultimately happens is you end up with your fire pit full of ash, right? In this case, you end up with the core of the star ending up being carbon. Now, it turns out these low mass stars never get hot enough to fuse carbon into one of the next elements. And so you just end up piling more and more carbon in the middle. And that carbon will eventually squeeze down so tight that it can't go together any closer. You can't push the carbon any closer together. And that's what we call degenerate matter. And that ultimately is what will become the remnant of the star, the core, and will be what we call a white dwarf. Now, these outer layers here are producing so much energy that they actually start to radiation winds, and radiation pressure starts pushing off the outer layers of the star. And so you end up with this planetary nebula ejection phase here, where basically the star blows itself apart very kind of slowly, pushing this material off. You're left with the little white dwarf core, which is made of what? Carbon. Right. Good job. And so on the HR diagram, this thing ends up, we now start to draw the path for the white dwarf, which is initially very hot. Remember, this thing was just inside the core of a star. It was very hot. So it's glowing very blue. And over a very long period of time, it will cool off, eventually becoming so cool that you can't see it. This is where you get some of the pretty nebula that we see in space. The one I chose to show here is my favorite object because I did my PhD dissertation on it in 2012. It's called the Red Rectangle. And this is what's called a post-AGB or post-asymptotic giant branch star, meaning this nebula actually, and it turns out it's a binary. So we haven't talked about everything we need, but basically the material that you see above and below here was from another star that went AGB, pushed off its outer layers, and now it's currently being illuminated by another star, and we'll talk about that in a little bit. I know I'm coming up on time here, so I'm going to figure out how to make this advance to the next slide. There we go. Other examples of this are the ring nebula, which you can actually see at our observatory here, including the little dot in the middle on a good night. You can see this little pinprick of light, and that's actually the white dwarf. So, all right, white dwarfs are about the size of a planet like the Earth, and Now, for time, I want to move on to, of course, what everyone's really here for is the high mass stars. But I don't have to spend as much time talking about them because we've already talked about the details. The big difference here is that these stars are much more massive. So guess what? You never get to that point where carbon can't fuse. So you never get this buildup. You don't have a helium flash. And so what happens is you use up, let's say, the hydrogen. Now you have a helium ball, but the whole star squishes down enough that helium immediately starts fusing into the next element, carbon. And you get layers, shells of burning. Sometimes people call this the onion skin model or something like that. And through this whole process of creating shells, you're getting more energy, you're getting expansion, you're getting contraction. And so what happens is these stars zigzag across the supergiant region, going from blue toward red, sometimes back toward blue, not always, and so on. And then they go boom, very, very noticeably. So this fusion process in the core goes until you get to the element iron. And iron's kind of special. The universe likes to do things that are favorable, energetically speaking. So when you fuse hydrogen into helium, you're giving off energy. But it turns out when you get to iron, if you wanted to fuse iron with something else, let's say iron, it turns out iron takes energy to fuse. No one likes that. No one likes to steal energy, right? So what happens is here you are, you're in the core of the star. You've had your hydrogen used up and so on. You've got layers of fusion happening above you. We're in the core and now we're this lump of iron, but we're not fusing. So are we making any radiation? No. So if the iron's not fusing, it does what the helium did in the low mass stars, and that is contract. It will contract until it can't. And so ultimately it will contract until basically you've pushed everything so close together that you've forced everything to be neutrons. And you've got the neutrons so close to each other, they can't go any closer. And that once again is what we call degenerate matter. And so meanwhile, all the layers above us are happily doing fusion. So we'll talk about the kaboom here in just a moment. And I just wanted to illustrate the process, how quickly this changed. Remember, these stars live for millions of years, which is very short compared to the billions of years of something like our sun. And so you start with these various, what we call burning, I mean fusion, but you get to the last one that makes iron. So the silicon makes nickel, which eventually becomes iron. And this takes 5 days for a 25 solar mass star. In 5 days, all of that silicon that was the core of the star has been converted into iron, basically. And at that point, it goes, it shrinks. There's nothing to push out. No hydrostatic, no pressure to push out. Gravity takes over and pulls it down. And this happens really quickly. It collapses until it can't, remember? And then it basically rebounds. So imagine dropping a hammer, right? It hits the floor and then it bounces a little bit. Now, this happens really quickly, and then all of the layers up above you that are fusing look at their feet and realize there's nothing below them, so they fall. And so you end up with the upper layers of the star falling down. You get the rebound from the core. They collide. It's a head-on collision, right? That's the worst type, right? That's where the energy is the worst. That's why you never want to have a head-on collision. Well, this collision rips the star apart, and that is our supernova. Once again, I'm technologically inept today for some reason. There we go. And what's left over after the big kaboom is very fast moving material. It runs into the material in the interstellar medium, which is the material between stars, and you get this brilliant light show. And they kind of look a little similar to the naked eye. They kind of look similar to the planetary nebula, but They are very different. And what's left over at the center is either a neutron star, more about that in a second, or a black hole, or maybe nothing. In this case, the Crab Nebula, which was a supernova that occurred in 1054 AD. I think that's right. We can look at it today and see a pulsar at the center, which is a neutron star that's rapidly spinning. And I don't think I have time to talk about the details of that. Supernovas are usually named SN followed by the number of the year that it was discovered. So this is Tycho's supernova, which was observed by Tycho himself in 1572. I'm having trouble, I can't copy that. But this link, which I'll try to get out like during questions or something, is actually a time lapse, basically. It's Hubble and all these satellites have been around long enough that we have an image of this from years ago and an image now, and you can see the motion of this expansion, which is, I think, just fabulous. So I guess trying to find the nice little wrap up here for you guys. I didn't get to binary stars, I don't think. So neutron stars, which is this leftover iron core that shrunk until it can't and becomes degenerate matter, which is a neutron star. If you remember, the white dwarf was about the size of the planet Earth. Neutron star is about the diameter of the length of Manhattan, which is an interesting thing to note, that neutron stars are city-sized. Right, so pulsars are just rapidly rotating neutron stars, and with that, the only thing we didn't talk about are black holes. Now, we don't have awesome images of those because, well, you can't really image a black hole. But you might say, but wait, we have images of black holes, and I have one slide for that. So I think for time, I'll skip the binary evolution. I can come back to it if Seth wants me to, but I will show M87 star, the black hole that was famously imaged by the Event Horizon Telescope, which is not a real telescope, but a virtual telescope made of radio telescopes around the world that collected a bunch of data, saved it to hard drives, flew those petabytes of data to, I think, MIT, where they use supercomputers to produce this image of the accretion disk around a black hole. So we're seeing material rapidly orbiting this black hole. It's getting very hot. Now, this is not the type of black hole that would be the result of a star. This black hole, as you see in the lower corner, is 6.5 billion times the mass of our own sun. And something I didn't mention in all of this conversation, the mass of a white dwarf is about, maximum mass is about 1.4 times the mass of the sun. The maximum mass of a neutron star is about 3 solar masses. And so a black hole that's left over from a star going boom is going to be on the order of a handful of solar masses, not billions. So I just wanted to leave that with a little bit of context and, of course, recent imagery. So without, I guess, further ado, I will say, are there questions?
Josh, we use the term supernova, you know, like Superman or whatever. Are there just garden variety nova?
There are, and for time, I didn't get a chance to talk about those, but those really come in the binary evolution part here.
Okay.
So if you have a star with a friend, and if those friends are close enough friends, then they can share. And so friends share and sometimes go boom. So in this case, it's all the same, except if one star ends its life before the other one, the material, as the star expands, can basically fall onto the other star. And then you get a couple things that can happen. One is a little bit of that material builds up on the star. Well, I guess in this case, it just transfers mass to the star. I guess where it was going here is, let's say now you got this situation where this star is evolved, as you see from top to bottom here, and then it starts dumping material onto a white dwarf, or it could be a neutron star. And what happens is some of that material builds up on the surface, And you notice this is a disk, by the way, just like when the sun was forming. That disk, some of the material falls onto the white dwarf, and you can basically end up with a little atmosphere that can get hot enough to fuse hydrogen. And so it's like a flash bulb going on. As soon as it gets hot enough and there's enough of the material, it explodes, and then that's it. These nova can repeat, sometimes regularly, sometimes not. And actually these explosions can trigger a different kind of supernova, which is the supernova of a white dwarf, which is often used to measure distances in the universe. And then you get the same sort of thing happening, same basic physics, different levels of energy that we're talking about, but you can get the same sort of situation with an evolved star and a neutron star, or an evolved star and a black hole. And there are famous examples of all those situations.
All right, great, thanks.
Complicated answer to your simple question.
No, that was great. All right, so let's open up to other questions. If you have, you can simply unmute and ask your question directly of Josh.
Or also feel free to type it in the chat. Stunned silence.
Am I unmuted now?
You
Yep.
are.
Right. I have a question. If a neutron star is not radiating because there's no fuel left to radiate, what is the energy that you see from like a pulsar, which is apparently a neutron star spinning around? Where's that energy coming from if it's just like a cinder of, you know, higher mass elements?
So just because it's not fusing doesn't mean it's not hot, doesn't mean it doesn't have energy. And so I didn't, I guess, hit on that well enough, but it's just like with the white dwarf. The thing that's left over is like a coal from the fire. It's very hot. The problem is, in space, there's no good way to cool. So things take a really long time to cool off in space. And so some of the energy that you would see in a pulsar is given off in the infrared, the visible. A lot of it's also given off from, I think I have a slide actually. Of course, it's being dumb again. But if it's in a system where it has a neighbor, some of that material could be falling on. There could also be other material just nearby. And what happens there is you get charged particles spiraling along the magnetic field lines. And it turns out that when you make an electron move, that produces radiation. And it's actually how a radio works. So, you know, at the local radio station here, what they do is there's voice, it goes into some electronics. That electronics also ultimately produces a current, which goes into an antenna. It oscillates electrons in the antenna. You can't see me because of the virtual background, sorry. It oscillates the electrons up and down, and that produces a wave. It turns out you can do the same thing if you have a magnetic field line and you spiral a charged particle around it. It can give off light, depends on the how fast this is going. It can give off light, it can give off radio. And so we can also see these pulsars showing up in the radio, which is, I do believe, how they were first detected.
Josh, Rebecca Gibney wants to know, as do most of us, what happens in a black hole? And that could be the subject of an entire talk, I suppose. But
it is. It's a subject of an entire talk. But the Cliff Notes version of that is so ultimately we'll use the supermassive black hole slide as a background while I chat. So what you're seeing in a situation like this is you're seeing material in another disk. So again, the same strategy here, same physics, that you have an object, you have a disk of material. That material is basically spiraling in slowly. Why is it spiral? It spirals because when you have a bunch of material close to each other and you're trying to make it orbit, well, they're at slightly different distances. And then they're bumping into each other. So bumping into each other, friction. Friction is lost energy. If you lose your energy, your orbit gets smaller. So this stuff slowly spirals in, or as we say, accretes onto the object. Now, in the case of a star forming, it adds to the mass of the star. In the case of a white dwarf, if it's from a companion star, it's, maybe causes a nova. In the case of the black hole, this stuff spirals in and ultimately adds to the mass of the black hole. Sometimes you get a jet of material, and we see these on galactic scales, and that's a whole other topic, something called active galactic nuclei. But once you cross what's called the event horizon, you have reached the point where the escape velocity is equal to the speed of light in vacuum. And since the speed of light in vacuum is the maximum speed that anything in the universe can travel, the thought is then light cannot escape. And so if it can't escape, then you can't see it, because we see things by reflected light. If I turned off my light here, you wouldn't see me because there would be no light scattering off of me. I suppose if you had an infrared camera, you could see me glowing, but what if I was so massive the infrared light couldn't make it out? And that's the situation there of a black hole. And then, of course, once you cross the event horizon, you're ripped to shreds. See Neil deGrasse Tyson talk about spaghettification. And then ultimately, you get to the point when ultimately the singularity is effectively all of the mass of the black hole is at a point, which is what makes it a singularity. And there, our current physics sort of breaks down. So we don't have a good answer for what happens to the atoms that once composed you. But a lot of people are very curious about what happens once you're totally ripped apart in that black hole. What happens to the stuff that was you? And it's perhaps also a philosophical debate. So hopefully that answered your question.
And gives us nightmares.
And it gives you horrible nightmares, yes. Any other questions?
These are great questions.
Ooh.
While we're waiting to see if anything else crops up, I did put it in the chat before, but our next talk is a month away, first Thursday of September. It's Eileen O'Donoghue from St. Lawrence University, Measuring the Universe with Exploding Stars. You'll see that a link for that registration coming up, the third in our Cygnus series.
It really doesn't want to let me copy that.
It is hot. Maybe it's getting too close to a star.
Yes, quite likely.
Tonight's talk will be on our YouTube channel within the next couple of days. So if you haven't subscribed to that, go ahead and do that, because then you'll get notifications of when these things are posted. And as I mentioned earlier, if you, I see Josh put that link up.
Yeah.
You want to explain again what that is, Josh?
Yeah. So at that link, which I just closed, you will see the supernova remnant, which I think is on the screen for you. I actually can't tell
Yes,
what's
it is.
sharing. Okay, it was. I just changed it by accident.
There it is.
So this is a supernova remnant. It's also false color. So this is one of those caution things in astronomy. If you look at the legend at the bottom, it says Spitzer Space Telescope. That looks in the infrared. Chandra, that one looks in the X-ray. And Color Alto, which is an optical telescope. So this is actually what we would call a multi-wavelength image of this hot gas from this supernova explosion that happened in 1572. And so it's expanding because it moved out from the star very quickly. And it's still doing that. There's nothing to slow it down. And well, I guess there's a little bit of stuff to slow it down, but not a lot of stuff. And so you can actually see in the animation that I just linked, it moving slowly over the course of a handful of years. I can't remember the number of years.
Great.
Oh, it starts in 2000 and goes till 2015. That was, so it's 15 years of motion, which is really, I think, quite cool.
Yeah, that's more than we've ever had before. So that something like that, that's great.
Is there time for another question?
You bet.
You had an image on the screen there of M something, which was the, it's not really a picture of a black hole, but it's an image that reveals a black hole, I guess.
Yeah.
And yes, now did I see also, like maybe you were looking at this disk straight on, but there's also kind of like a disk of fainter red from upper left to lower right. Is that something to do with the black hole, or is that just an artifact of
Yeah.
the
I
of
can't
the
tell.
way they made this image?
Yeah. Can you see my mouse or not? I can't tell.
Yes.
Yes.
Okay, great. So you're talking about that, right?
I'm talking like from the upper left angling to the lower right is kind
Yeah.
of like
Yeah,
maybe
you're
a
talking about
faint disk that's sort of that you'd be seeing edge on.
Yeah, no, I don't know for sure, but to me that kind of looks like an artifact of the way the image is produced.
Okay.
Because I also kind of see like a blob here, here, and here.
Yeah, sort of sticking out on the sides. Yeah.
Yeah, I think, I mean, I could be wrong, but I think that, in fact, they have an updated image of this, which I didn't grab for some reason. And I don't think it has that, but I think you'd have to check. But yeah, I would say, so this disc is kind of, it's a little tilted, I think. Not so it's not exactly face on, but maybe kind of like that, maybe.
And that would be the accretionary disk that's orbiting around the black hole.
Around this supermassive black hole. And the name in the upper left corner, because you asked, is, so this is Messier 87, which is this is actually in the center of a galaxy called M87. The star thing there is how we denote the supermassive black hole at the center of that galaxy. For example, the supermassive black hole at the center of our galaxy doesn't quite follow this naming convention, but it has the asterisk. So our black hole's name is SGR A, capital A, star. And SGR stands for Sagittarius, which is the constellation in which the direction of the center of the universe is, or sorry, center of our galaxy is. And A, I'm not sure why it's A, probably because it's the first one, and then the star.
Right. Jeanette Scott wants to know, am I understanding this right? Not all supernova result in black holes.
Correct. In fact, you know, a fair number of them just result in a neutron star. So if I navigate back to that here, yeah, so this is this little summary slide. Oh, computer's so slow. So starting from the protostar, you know, various evolutions here. So if we just look at the high mass stars, which start here with the blue supergiant, they go to red giant, or, you know, probably even supergiant. And you can have a type, well, they call it type 2 supernova, which is what we call a core collapse supernova, which is the, you know, the death of a star. And that can result in a neutron star. It could result in a black hole if the mass of the leftover core is greater than the maximum mass of a neutron star, which is 3 times the mass of the sun. And there are physical limits for why there's a maximum mass, and that had to do with this so-called degenerate matter, that you've pushed things so close together that what's keeping it from collapsing, the new pressure that's keeping it from collapsing, is called degeneracy pressure. And it's basically that you're trying to push 2 particles that don't want to be in the same place together, and so they basically hold each other up. But if you overpower it, collapse. And so yeah, so not all supernova make black holes. Supernova can be used to calculate distances, of course, and the type that can be used to calculate distances are generally the white dwarf supernova, which I didn't spend a lot of time talking about. But if you've got a binary star system, you have a white dwarf and a star that's trying to go through its, you know, red giant phase. It can dump material onto the white dwarf, and if you push it over its limit, it will explode. And it explodes at almost exactly the same mass, 1.4 solar masses. So it always has a consistent brightness. So you can use it to measure distances, or at least that's what people hope they can use it for. The problem with all the other supernovas is you don't know the mass of the star that is exploding. So we don't necessarily know how bright they should be intrinsically, like if you had looked at the brightness on the bulb. But I think there are some people now trying to use those as distance measurements as well, but I'm a little outdated on the literature. So thanks for the question, Mark.
Great. Another link I just sent up again. Anybody interested in registering for our astrophotography conference and maybe imaging some of these planetary nebula or other stars that we have up there just waiting to be photographed. You can check that out. And of course, again, if you're interested in making some kind of donation, feel free to use that link. If you're thinking about something more sizable, please don't hesitate to give us a call. And with that, Josh, I really want to thank you. Jeff Bridges is out. You are officially the star man now in my book. Thank you so much for doing this. This was a lot of fun, and really enjoyed it, as I think most did here. So thank you.
It's always so hard to tell on Zoom, but I hope everyone had a sign. So.
Yeah. I see some applause coming already in the in the reaction categories there. So. All right, with that, everybody, we'll see you hopefully back here for Eileen O'Donoghue on September 2nd. Look for that link coming up within the next week. And clear skies to everybody. Thanks for coming. Good night.